Hello, I'm Damien Pousse, and I'm going to present joint work with Denis Kupperberg and Laure Limpino about the computational content of cyclic proofs. I will start by recalling the Curry-Ward correspondence and how we can program with proofs in a very simple sequent calculus we designed for this work. Then I will explain how to deal with functions on lists or natural numbers, these inductive data types, and showing that we can represent recursive programs using cyclic proofs. Then I'll switch to the expressive power of those cyclic proofs in various settings. In particular, I will relate them to Gödel system T. Let us start with the second calculus which we shall use, of which a few rules are depicted here. Here are the rules for sum types or disjunctions. So you have two rules for proving disjunctions by proving either the left-hand side or the right-hand side, and a rule for analyzing a disjunction on the left, where you have to provide a premise for each possibility. And also note that the identity axiom is quite constrained here, because the environment should only contain A in order to deduce A. So equipped with those rules, let us do the following exercise, and let us prove or represent those functions here written in pseudo-ML code as proofs in this sequent calculus. So here we have a function of type a plus b to b plus a, which proceeds by pattern matching on the argument, and we can represent it as follows. So we start the proof with a plus b proves b plus a as goal. Then we do a pattern matching, a case analysis on this formula here, and so we get two sub-goals, a proves b plus a and p proves b plus a. In the first one, we want to produce this constructor here, and so we use the right introduction rule for plus here, which is the second one, and we get to prove a proves a, which is provable by the identity axiom. And on the right-hand side, we use the other right introduction rule to get b proves b, which we prove with the identity. Here is a very simple variant where there is a spurious C here, which is proven in a very similar way. A plus b proves b plus a plus c. Again, I proceed by case analysis on this value here. If it's an A or if it's a B. If it's an A, then I must go right first here, so I use the corresponding rule for plus on the right. A proves A plus C, and this corresponds to this constructor. Then I use the other one, which corresponds to this constructor, and I go left. A proves A, and then I use the identity, which corresponds to the fact that I'm using the variable here, which was given. And similarly, for the right, it suffices to go left, and then to use the identity axiom. This was for sum types. Now let us look at product types, whose rules are given here. So you have a rule for product on the left, where product just becomes a comma, and a rule for constructing products on the right, where you have to provide a proof of A and a proof of B, but note here that the environment is split. That is, you must split your environment into two pieces, one for proving A and one for proving B. And this is related to the fact that identity is quite constrained here. So equipped with those rules, let us do another exercise about products. So the first one is about the second projection, so let me try to prove it. A times B proves B. I can transform this product into a comma, A comma B proves B. And here I cannot use the identity axiom because I have a spurious A here. So I must use a structural rule here called weakening just to remove this A. So this is weakening. And then I conclude with the identity. Now for the second example, this diagonal function, I will need another structural rule. I want to prove A proves A times A. But now if I try to use directly my rule for product here, I must split the context into two pieces. So one of the two pieces must be empty and I won't be able to finish. So beforehand, I need to duplicate this A, and this I can do with the contraction rule, which duplicates A into A, comma A. And now I can split the context into two pieces, one A, which is given to the first one, and then concluded with the identity, and the second A, which is given to the second one, and then I conclude with the identity. Finally, let us do the last example, which is a swap operation. So I want to prove A times B proves B times A. I transform this product into a comma first, and then I must reorder this list before splitting it. And this is to this end that I use the exchange rule, X, to move to B, comma A proves B times A. And then I can split B with B and A with A. So we have seen that we need some structural rules, weakening, contraction, and exchange. There is also one missing rule in this system, which is well known. This is the cut rule. And let us exemplify it now. You can use it to implement composition. So here, I want to compose two functions. What can I do? Well, I can use a cut to prove A proves C by going through B. So I will prove A proves B, and then B proves C. And for this one, I will use the proof for F, and for this one, the proof for G. On this example, you can understand what is the computational content of the rule here. The idea is that you get arguments here for A, which are passed here to the proof of F, which will return eventually proof of B. This proof of B is passed here to the proof of G, which returns a value in C, which is the return value of the full proof. Another important thing to notice with such a system where structural rules are explicit is that we should be careful about them. Here is a proof of A to the cube proves A to the square. And if you think in terms of functions, there are several functions proving this simple formula. And in fact, here, we don't know yet whether this should be A1 or A2 or A3 here. It can be any of them. And this we can learn by looking carefully at the ancestry graph of the proof. So what is this ancestry graph? These are those lines. Here, this A comes from this one, and in turn, this one comes from this one. Similarly, this A comes from this one, this A comes from this one, this A here, here, and here, due to the exchange rule, they are swapped. And here, due to weakening, this one gets lost, and this one continues there. And in the end, we can understand, by looking carefully at this ancestry graph, that the first element of the returned pair actually comes from A1, the first argument. So this is A1. And similarly, the second element of the pair comes from the third argument, that is A3. Okay, so this was for basic data types. And now what about lists and natural numbers? So in most programming languages, those are equipped with constructors, like nil and cons for lists, and zero and successor for natural numbers, and pattern matching. And those constructs are really easy to obtain in second calculus. They are just those rules. So here are the rules for lists. This is pattern matching on lists. That is, in order to exploit a list, you must deal with the empty case and with the non-empty case. And you can produce the empty list in the empty environment and produce a non-empty list in an environment which you have to split, very much like for the product. And those rules, in fact, just come from the fact that A star is isomorphic to 1 plus A times A star. the rules for natural numbers are obtained in the very same way. And now, with those rules, we can start coding other functions, like this emptiness test for list. So if I want to represent it as a proof, well, this is a proof of A star to 2, which proceeds by pattern matching, so this is star left. I must provide something for the empty case and something for the non-empty case. In the empty case, I want to return true. We abbreviate the corresponding proof like this. In the non-empty case, actually I get access to the head and the tail of the list, but I don't care about them, so I must weaken them using weakening. And then I can return false. Okay. But as you expect, this is not enough. If you want to program with lists or natural numbers, you need more. You need some form of recursion. And for example, if you want to program those two functions, you need to do something. So let us try to represent even as a proof. So even, it's a function from natural numbers to booleans again. So nat to 2. And it proceeds by pattern matching on the argument. So this is nat left. In case it is empty, it must provide something. So here it will return true. Otherwise, it's not empty. We proceed again by case analysis, because here this is nested pattern matching. We must provide something in case this value is 0, which means that this one is 1. So here this is the value for 1, this is false. And in case this one is a successor, we have to answer something. And if this one is a successor, then this one is twice a successor. And what do we do in this program? Well, we do a recursive call, which we can just implement using a back pointer. We say, in this proof, when we reach this point, we go back to the root of the proof. Alternatively, we can just think of it as the infinite unfolding of this pattern into a comb-shaped tree, and we get an infinite proof which represents this function. And this is why we claim that we can represent recursive functions as cyclic proofs. Now, a difficulty with recursive programs is that they may fail to terminate. And this is well known from non-well-founded proof theory. These cyclic proofs may be unsound. So we need to do something in order to forbid invalid proofs. And the standard technique consists in using a validity criterion. It's very standard in non-well-founded proof theory. And this criterion, in our case, can be stated as follows. Every infinite branch must contain a valid thread. This is a Bucci condition on the infinite branches of the proof, which you can decide in p-space using Bucci automata algorithms. And we get this theorem. All valid proofs denote total functions. Now let me briefly explain what is this validity criterion, and in fact what is a valid thread. So intuitively, threads are those lines which we did draw here on the proof. There are those lines corresponding to the ancestry graph of the proof. And the thread is valid every time if it visits principal steps infinitely many often. So let me show this on the function even here, which we have seen before. This function has only one thread, which is here. and which continues along the branch, and which is principal here, because here we do a case analysis on the followed formula, here and that. It is also principal here, because again here we do a case analysis. And also here, because actually here, this is just the same thing as there. So this thread is along the infinite branch, and it is principal infinitely many often. So it validates the branch, and since there is only one infinite branch in this proof, the proof is valid. Now let us consider non-examples. Here are two proofs, which in fact are not valid. In the first one, the threads are as follows. Here there is a case analysis on the first argument, so a thread which is principal here, but then due to the cut, the thread goes left here. And then the thread restarts from here, and will be principal here, and continue. But the important thing is that the thread is cut when we go along this branch here. Here it goes left, it doesn't go right, so the thread is cut. And even so, it seems we go infinitely many often through principal steps, this is not okay, because the thread is not maintained. So this proof is not valid, and in fact, if you look at it carefully, you would realize that it corresponds to a non-terminating function. A more complex example is on the right here. It starts with a contraction, and the threads are as follows. So this A comes from there, and goes there, and then continues in the branch. But this A star also goes on the right, here, because of the contraction. And there it goes like that. And again, it continues along the branch. And now this star L step actually was a case analysis on this star formula. So there is a thread going on here, which stops here because of the weakening, and which is principal at this point, because of the case analysis. Now in this proof, there are many infinite branches, because you can alternate in many ways between those two cycles. But all threads, if you want them to be principal, you need to go there and thus to cut the thread. Therefore, none of these infinite branches may be validated. And thus, the proof is invalid. Okay, so now that all of this is set up, let us look at expressivity. The first result is the following one. If you focus on regular expression types, that is, you only have products, sums, and lists, and if you forbid structural rules, then you get that there is a cyclic proof of E proves F, if and only if the language of E is contained in the language of F. So in fact, you can prove all regular expression containment using cyclic proofs without structural rules. And the proof of this is fairly easy. A second expressivity result is the following one. Let us focus on formal languages, that is, sequence of this shape. It is A plus B plus C, a finite alphabet, to the star, proves 2. I claim that these are formal languages, those are their characteristic functions, those are functions from list of letters to booleans. And here on this slide, I'm reasoning without the cut rule. What we can get in this setting is that in the affine case, that is without contraction, we get precisely the regular languages. In fact, a cyclic proof without cut in this setting is basically a finite automaton. And in the general case, that is with contraction, it's a bit more complicated. A proof is basically a multi-head automaton, and we could prove that actually we characterize log space languages. Now let us focus on the expressivity results from the present paper, the present work, which is mainly about comparing cyclic proofs for arbitrary functions. The first observation is that you can encode any primitive recursive function in the affine fragment of system C. That is, you don't even need contraction to encode primitive recursion. And if you allow contraction, then you can encode the whole of Gödel system T. which is a simply typed lambda calculus with an iterator for natural numbers. Of course, in order to do so, you need also to add arrow types to system C, because this is a lambda calculus, there are higher order functions here. But this is really straightforward to do. But on a concrete example, we can also implement Ackermann's function in system C. Ackermann already belongs to Gödel system T, but we can actually do better here, because we don't need arrow types to implement it. And let us see this. Here is the standard recursive definition of Ackermann, and here is a cyclic proof for it. You can see that the proof only uses natural numbers as formula. There is only one formula in this proof, and it really mimics the recursive definition. It starts with a contraction, and this is because also we start here with a pattern matching on n. In this branch, we will use both n and the predecessor of n prime. So we need to anticipate this and duplicate the value of n. And afterward, we do a case analysis on one of the two copies, the first one. If it's 0, then we must return the successor of the second argument, which is what we do here. If it's a successor, then we must do a case analysis on the second argument. If k, the second argument, is 0, then we must do a recursive call on n prime, which is there, and 1, which is obtained by a cut, via a cut. And if k is not 0, then we must do two nested recursive calls, which we implement via a cut. So this is the inner call, and this is the outer call. So now, why is this proof valid? Why does the corresponding function terminate? Well, we have to draw the threads in order to understand this. So here they are. And if I abstract a little bit more, I get this picture, where we again really recognize the structure of recursive calls in Ackermann function. I want to compute a and k, and I will certainly do calls on n prime 1, n minus 1, 1. Here, this is this recursive call, but also on n and k minus 1, this is this one, and on n prime and the result of the previous call. This is the outer call. And now, if you remember the validity condition, let us consider all infinite branches, which may alternate arbitrarily between the three back pointers here. If they go infinitely often through this one or this one, then we can use the green thread by being careful to go left every time the next move, the next cycle is this one, because when we go along this cycle, we cut the green thread, so this is bad. And we must be careful to go left in order to keep the thread alive. And in the other case, that is if eventually we no longer go through this one and this one, that is we eventually go only through this loop, then we can use the red thread. So this is why this proof is valid and the corresponding function terminates. Now let us back to Gödel system T. I've said that we can compile pretty easily system T into system C, and system T is well known to be equivalent for functions on natural numbers to those functions which are definable in Peano arithmetic. In the affine case, I've told you that we can encode all primitive recursive functions, and actually there is an affine version of T which was studied by Ugo Dal Lago, and through which the previous compilation factorizes. In fact, Ugo Dal Lago has proven that affine T contains precisely the primitive recursive functions. So at this point, it would be nice if we could get upper bounds and relate C and affine T to either T or those classes of functions. But this is really hard. In fact, going from C to T is a decompilation process. We need to decompile cycles, arbitrary recursions, into basic iterators, to decompile goto programs into programs using only for loops. And this is a well-known problem in logic, which consists in translating infinite descent arguments into induction, which is difficult and which has both positive and negative instances. And in our case, we still don't know how to do it, how to solve it in the presence of contraction. Still, we managed to do it in the affine case, and this is difficult already. And we proceed in two steps. We exhibit a hierarchy between the cycles of the proof, and then we translate the proof bottom-up and recognizing blocks of mutually primitive recursive functions. And those mutually primitive recursive functions, we encode them into plain primitive recursive functions using additive pairs, which is a new connective which we need to add to the system, which is well known from linear logic. So we get this picture. We don't know how to decompile C into T, but we know how to decompile affine C into affine T with additive pairs. But now, in order to reach those two classes of functions, we need different tools. And what we use there is reverse mathematics. So this is an area of logic where people study the relative strength of various logic systems. And here are two systems which are quite important, ACA0 and RCA0. RCA0 actually is a very constructive version of arithmetic, where you can only reason about recursive sets. And ACA0 is the extension of RCA0 with conics lemma. And those theories have nice properties. In particular, they enjoy extraction theorems, where if you prove a property of the shape for all exists in ACA0 or RCA0, then you can extract a witness of those properties, which is either Peano definable if your proof was in ACA0, or primitive recursive if your proof was in RCA0. And this is what we use in order to get our upper bounds. In fact, we define a small step operational semantics for system C, which we prove to be weakly normalizing in two ways. We do a proof in ACA0 in the general case, which is an adaptation of reducibility candidates. And we give another proof for the affine case, which works only in the absence of contraction, but which can be formalized in RCA0. And this one uses a multiset ordering over a finite order. So in the end, we get that functions on natural numbers from C are all Peano definable, and similarly, functions on natural numbers from affine C or affine T with additive pairs are all primitive recursive. And by the way, this is actually a generalization of this result by Dal Lago, because his proof did not scale with additive pairs. To summarize, we have seen with a single sequence system inspired from linear logic and with its cyclic interpretation how to characterize various classes of objects. We have seen how to characterize regular language inclusions, but also regular languages themselves, as well as log space languages. For first order functions, we have seen how to obtain primitive recursive functions and Peano definable functions. And for higher order functions, we have this nice correspondence between affine C and affine T, but we still don't know if it is possible to decompile directly C into T, that is recursion into iterations. Thank you for your attention.